Good afternoon again, everyone. Thank you very much for coming to the HamSCI workshop. Our chair and host for this next session is Jesse Alexander, WB2 IFS. Come on out, Jesse. And I had the pleasure of meeting Jesse last year, first at the Tapper workshop, where I learned that he was running this NRAO ham radio project.
Indeed.
And he has many wonderful students that he has been teaching across the entire United States, right?
Yes, I do. And four of them are here today. They'll be here today.
They'll be presenting shortly, right?
Yes, they will.
They're still in the green room.
They're still in the green. That's it. They're in the green room. They're still getting ready. Yes.
Right. So anyway, I'd like to thank Jesse for coming and for bringing his students here. And Jesse, you can take it away and introduce people for the rest of the session.
All right. I'm glad to be here, and thanks again, Nathaniel, for inviting me again. All right. Let's get the show on the road. We're going to start off first with Nick Patch. Whiskey. I cannot believe this. I'm sorry, folks. This is like that Bill Gates moment, right, where our devices are attacking us. Anyway, without further ado, let's get started. Nick Hall Patch, Victor Echo 7, Delta X-Ray Romeo, will be speaking to us about early results from the 2023 Eclipse medium wave recordings. All right, take it away.
Thank you, sir. Okay. Jesse's already given the title off, so let's see if we can actually pulse her through to the next one. We can. Excellent. Okay. This talk's going to be about the data generated by HamSCI volunteers at 14 sites in North America and in Europe, recording the entire medium wave AM broadcast band using software-defined radios. We'll cover some details. The data from these recordings has now been pre-processed to allow researchers to easily find evidence of eclipse effects upon carrier signals of medium wave broadcasters by using visual examination. Examples will be given of how this data might tell researchers more about the eclipse effects. Let's start with a sort of a ground-up introduction. The medium wave AM broadcast band is assigned between 525 and 1705 kilohertz, and these are basically entertainment stations providing continuous signals, many 24 hours a day. Amplitude modulated signals, as any people with an engineering background will know, consist of a carrier signal with sidebands, as we can sort of see here on the waterfall. Sidebands are variable. The carrier signal is basically stable and stays that way like a steady RF beacon. Any change in that beacon's amplitude or frequency at the receiver is likely to be caused by changes in the path between the transmitter and the receiver. During a solar eclipse, the brief period of darkness along the path of the eclipse can allow such signals to temporarily travel much further than they normally would during the daytime. Now, software-defined radios can record the entire medium wave broadcast band, and by using suitable software, the resulting files can allow us to visualize the propagation-induced changes these carriers undergo over time, including changes in signal strength and shifts in the frequency of each carrier. Now, I have a brief example here of the visualization software. Up the top, the x-axis is the gradations are in hertz, although the resolution is actually more along the lines of 0.1 hertz. Time is on the y-axis. This is actually during the eclipse period in Phoenix, Arizona by KF7NP, and the vertical lines are various carriers on the frequency of 1650 kilohertz, and the sort of standard approach of waterfalls, the sort of hotter colors indicating the stronger strength of the carriers. Okay, so as part of our introduction here, all 14 of those sites produced recordings during the eclipse. 12 sites also included the local sunrise and or local sunset period of the eclipse. And 12 of the sites also included data from the same time as the eclipse on the day before or day afterwards. 6 of those sites had data using SDR locked to a frequency standard that was disciplined using GPS signals, and 3 others included a signal from its frequency standard in their recording, simply because the SDR was not capable of hardware input from that reference. And finally, the bulk of the sites also had their clocks, computer clocks, updated using network time protocols, so they were quite accurate. Since the eclipse, all 10 terabytes of that medium wave data has been gathered and archived. Preliminary processing has been done using Carrier Sleuth, an inexpensive commercial software package. All signal sync data from each participant is now available to a 0.1 hertz resolution over an 80 hertz span around each of those broadcast band channels. In addition, for all those channels and from every participant, useful visualization of the signal variations during the eclipse is now available, as well as for all other time periods recorded at each site. So we'll go back to this slide, which it was generated by this Carrier Sleuth software, and it's just an example of one channel. And again, just looking at the display here, this visualization, you can see that you have, like the color becoming red around 1630, which is the peak of the eclipse, is obviously getting stronger and then getting weaker again as the eclipse passes. And this has been seen at a number of sites. Whoops, boy, that was pretty clever. We'll have to go back a little bit. Hit the wrong button. This is one of those ones that didn't take any time at all. Okay. It was arbitrarily decided that carrier that increased in strength by at least 10 dB during the duration of the eclipse would now be deemed to be influenced by the passage of the moon's shadow. So did our participants see the eclipse affecting their normal daytime reception? 6 of the sites did indeed report that. However, others did not. So looking back at our map of participants, what locations were influenced mostly by the passage of the eclipse? Well, take that map of the participants, flip it on its side, and you can see that in the West Coast, we had, various participants had dozens of the channels had signals that were that they could see signals that had been influenced by the eclipse passage. However, up in the northeast United States, there were very few of these people were noted, noted any effect at all from the eclipse. These were in the 50% and less obscuration, but it's more likely that it's simply that the reflection point from target stations was simply that the D region was still too ionized at such a low level of obscuration. It'll be interesting to see if this rule of thumb obtains during the upcoming total solar eclipse, because many of the same monitors will be taking part, those various blue circles there indicating monitors. And the path of the eclipse is going to favor those in the eastern USA considerably more than in the west. Okay, visualizing the recorded data, I'll give an example here. Once these channels affected by the eclipse have been identified, the processing software allows us to get a good view of any signal enhancement as the eclipse progressed. The following visualization is from near Sacramento, California by KE6EE on 1520 kilohertz. The recording includes both the time period of the annular eclipse as well as the period during the ionospherically active period around local sunrise at 1413 UT. Richard also recorded this same time period on 13th of October to provide a comparison. Okay, so this is the control day, October the 13th. And you can certainly see local sunrise is that pink line, horizontal line. And before local sunrise, the carriers were shifted and spread out by the effects of the rising sun. And you can see with some fairly obvious multipath going on there as well. And after sunrise, those signals declined quite rapidly. And we'll do a quick identification of the signals. From the left, radio station KVEN in Port Hueneme, California, near Los Angeles, with the Wiggly Line. And then KKXA, Snohomish, Washington, which is near Seattle, and KGDD, Oregon City, Oregon. These are the sort of dominant signals on that channel. Okay, so now we'll look at October the 14th, and we have the circle around the eclipse times. And you can see that the carriers on KKXA and KGDD, they both increased in strength around maximum eclipse maximum, or just before, and then decreased again. We'll flip back to October the 13th again. We just see those signals had gradually faded away. So let's actually compare the signal strength on just one of them, KKXA, which is this is the signal strength on the 13th on the left-hand side. You can see pretty much what you'd expect. As sunrise approaches, the signal starts to decline and then declines as the day starts to progress. However, on the day of the eclipse, there's a decline as sunrise approaches, and then as the eclipse starts, the signal strength again increases, in fact, is stronger, really, than the signal before sunrise, and then fades away again as the eclipse fades. So both KKXA and KGDD carrier strength increased and then decreased during the course of the eclipse. However, on the left-hand side, KVEN, no increase at all. It sort of just act like a normal day. So what's the difference? Okay, looking on a map, KKXA and KGDD, both in the 80% obscuration range. Their signals cross the path of the annular eclipse. However, the path from KVEN, it did not cross the path of the eclipse, and it was at 70% obscuration. In addition, it may just be that there was absolute, like even if the D region had been wiped out, it may just not have been in a position to get a decent skip because it's closer. But those are other suppositions. A couple of the HamSCI objectives might be supported using these SDR recordings. One of them is the eclipse ionospheric response symmetric with regard to onset and recovery timing, which is we have sort of mentioned before, and the other is how similar is this eclipse effect on propagation to that of the daily dawn and dusk terminator passage. These topics will come up again and again, I imagine. Okay, so we'll start with the second one first, and just visualizing in KE6EE's 1520 kilohertz data shows spectral spreading and some shift of frequencies, definitely around sunrise. However, during the eclipse itself, it's just carrier increase. There really is not much, well, certainly nothing like what happened at sunrise. And this is just from visual examination. However, the recording of 1520 kilohertz is just one example. If we look at 1,000 kilohertz on the same data set, this is KNWN from Seattle, so virtually the same place 1520 kilohertz is coming from. There's very little difference in the carrier characteristics during local sunrise and during the eclipse enhancement period. It just, there's practically no spectral smearing, no multipath or anything during sunrise period. However, we have to note that the medium wave band has a 3-to-1 frequency span, and comparing 1,000 kilohertz and 1520 kilohertz is like comparing 20-meter amateur band propagation to 15-meter propagation. You wouldn't expect them to be the same. And even close examination of KNWN's carrier shows perhaps some spectral smearing, but you're going to have to do a fair bit more work on there to sort of define, anything that you can hang your hat on. Beyond frequency differences, perhaps we also need to think about the signal path from the transmitter to the receiver relative to the angle of the sunrise or sunset and a terminator, which is somewhat different there, and also the angle at which that signal path crosses the path of the eclipse. And now let's go to the first scientific supporting. So we have is ionospheric response symmetric with regard to onset and recovery timing? We can't tell that directly, but we can certainly say the visualization alone will tell us that as the eclipse starts and then maximizes and then finishes, that's not exactly what you would call symmetrical. And carrier sleuth itself can generate a graph of signal strength versus time for a quick first look, but it's just a snapshot. But you can definitely see that increase from the slide somewhat earlier. The same software, however, can deliver CSV files, signal strength versus time, for a 0.1 hertz slice spectrum, which can allow us to start processing the data in earnest. And just have a sample there of a CSV file, every 15 seconds updating dBm signal strengths. This file can be ported into an Excel spreadsheet or other software for further analysis. And from KE6EE's raw data, you can see 1520 kilohertz, the red, and 1000 kilohertz, the blue, from sunrise through to the eclipse period. And now we can actually zero in on one of the data sets alone, 1000 kilohertz, and it's fairly straightforward to get the slope of signal strength versus time, followed by a slope for the decay and strength. We have the numbers here, and definitely the increase rate in dB per minute is considerably slower than the decrease. And there's over 3 ratio of decay to increase. But we repeat the exercise for KKXA signal on 1520 kilohertz. We have a similar rate of increase, but the rate of decay is considerably slower. It's and the ratio is under 2. We're definitely looking at a different rate of decay, and quite obvious if you actually look at again a visual chart of the signal strengths. So once again, the effects of the eclipse seem to have depended on the frequency of the received signal. So, of course, that's from one data set, looking at 2 received signals, differing frequency, but transmitted from essentially the same locations. But there are over 400 distinctive enhancements flagged in the 14 data sets gathered. So there's a lot more analysis to be done. And on top of that, in a couple of weeks, there's going to be a lot more data to examine. Having gone through some of this, there's a what's next question. And in the analysis of KE6EE's recording, it's possible to identify the target carriers, from the SDR recordings, but that's because the audio, there was actually audio being delivered by those carriers, and there was station identification on them. So, the location of that station is available in public databases. However, going through all those data sets, many of the carriers of interest in other recordings, we may not have identifiable audio in the SDR recordings. We've just got a carrier, basically we have the exact frequency if we're lucky. So how are we going to find the locations of those transmitters associated with those fleeting carriers? Many of the participants use GPS-based reference signals to discipline their SDRs, and that means that the carrier frequencies observed should be accurate within plus or minus 0.1 hertz. A subset of medium wave DXers archive the exact frequency of radio stations as an aid to identifying rare DX heard, as many of the broadcast stations are stable to that rate. So we're going to encourage such DXers who may not be actually participating in the eclipse observations to record a short period during the upcoming eclipse day at the top of the hour when stations are supposed to identify themselves, and to submit that SDR file as part of the eclipse archive to aid in identifying mystery carriers. In conclusion, well, we did successfully record a whole lot of medium wave data. Initial pre-processing of this data has made it fairly easy to examine it for influences by the eclipse. Some of the HamSCI science objectives might be met with this data, and we provided a couple of examples. Ways will need to be devised to identify the origins of many of these enhanced carriers. And no effort has been made yet to link these observations with possible ionospheric processes. Like Gwyn said a little earlier, we need to talk to the scientists about that. Okay. Thank you, and special thanks to the dozen other HamSCI participants in the 2023 Medium Wave Recordings event. They will know who they are. Okay.
Great. Thank you. Thank you.